The first step is always check to see if this rational expression is proper. It is proper in this case because the degree in the numerator is 5 and the degree in the denominator is 6. When we distribute x squared to x to the fourth, the highest degree in the denominator is 6. So it is proper. We then proceed with factoring the denominator only. X squared minus x times x to the fourth minus 2x squared plus 1. X squared minus x is x times the quantity x minus 1. X to the fourth minus 2x squared plus 1, we recognize that this is x squared minus 1, the quantity squared. This is x times x minus 1 times x squared minus 1 times x squared minus 1, which we can factor x squared minus 1 further. X squared minus 1 is x minus 1 times x plus 1. And the second x squared minus 1 is x minus 1 times x plus 1. Thus, we have a factor x minus 1 being repeated 3 times, and the factor x plus 1 being repeated 2 times. All of these are linears. X linear, x minus 1 linear, x plus 1 linear. To set up the partial fraction decomposition for the given rational expression, we see that there are 1, 2, 3, 4, 5, 6. There are 6 factors in the denominator, so we would need 6 terms. The first term with the denominator x, the second term, denominator x minus 1, and then x minus 1 squared, x minus 1 cubed, x plus 1, x plus 1 squared. Keep in mind that for repeated linear factors, we would need to increase the exponent of the linear factors by 1 each time until we have that many repeated factors. X is linear, so we only need a coefficient in the numerator. X minus 1 is linear. X minus 1 squared has linear factors, so we only need a coefficient in the numerator. X minus 1 cubed has linear factors. X plus 1 is linear, and x plus 1 squared has linear factor x plus 1. Thus, this is the setup for the partial fraction decomposition. To find the coefficient a, b, c, d, e, f, we rewrite the given rational expression using the factored form in the denominators, and we use the cover-up method to find as many coefficients as we can. We won't be able to use the cover-up method for all of these coefficients. To find the coefficient a, we would go back to the factor form and cover the factor x, where x is the denominator of the coefficient a. We then plug in an x value that would make the covered factor 0. This is the reason why we covered it, because the value that would make this covered factor 0 is x equals 0. If we didn't cover it, then we would end up with 0 in the denominator. So we covered x and plugged in 0. A is 0 to the 5th plus 1 over, remember, we covered the factor x already, so we don't plug 0 into x. The denominator is 0 minus 1 cubed, 0 plus 1 cubed, and so a is 1 over negative 1 times 1, negative 1. We won't be able to use this cover-up method to find the coefficient b, which is the coefficient in the numerator of x minus 1. Because if we plug in 1, then we would end up with 0 when we cover only one factor of x minus 1. We can find the coefficient d because we would cover the entire x minus 1 cubed. When we cover x minus 1 cubed, we would plug in x equals 1. Thus, d is 1 to the fifth plus 1 over 1. Remember, we covered the factor x minus 1 cubed. What left is x, we plug in 1, and then x plus 1 squared, we plug in 1 into x as well. 1 to the fifth is 1, 1 plus 1 is 2, 2 over 1 plus 1 is 2, 2 squared, 1 times 2 squared is 4. D is 1/2. Similarly, we won't be able to use the cover-up method to find E, because otherwise we would only cover one factor of x plus 1. Thus, to find f, we would cover x plus 1 squared. F is now, we plug in -1 because the number x that would make the entire factor x plus 1 squared 0 is x equals -1. -1 to the fifth plus 1 over -1 times -1 minus 1 cubed. This is 0 over any number will be 0. So f is 0. Thus, out of 1, 2, 3, 4, 5, 6 coefficients, we can use the cover-up method to find 3 coefficients already. We then update the equations with these newfound coefficients. It is not a coincidence that f is 0. We get rid of the factor x plus 1 squared, but then the least common denominator is now missing an x plus 1 squared, and that is because x to the fifth plus 1 can be factored as x plus 1 times x to the fourth minus x cubed plus x squared minus x plus 1 using the binomial theorem. Notice a factor of x plus 1 cancelled out. Thus, the least common denominator is actually x times x plus 1 times x minus 1 cubed. It must be true that x to the fourth minus x cubed plus x squared minus x plus 1 over x times x minus 1 cubed times x plus 1 must be the same as -1 over x plus b over x minus 1 plus c over x minus 1 squared plus 1/2 over x minus 1 cubed plus e over x plus 1. To find the remaining coefficient b, c, e, we will need to find the least common denominator of the right-hand side and combine them. This least common denominator is the same as the denominator on the left-hand side. It is ironic that we decompose the fraction and now we combine them, but we need to do that so that we can compare the two numerators where the unknown coefficient b, c, e are. These coefficients are in the numerators. To combine these fractions, we would need the same least common denominator for each one. To do that, we would multiply the numerator with any missing factors in the least common denominator. -1, the missing factor is x minus 1 cubed, x plus 1. With b, the missing factor is x, 2 factor x minus 1, and 1 factor x plus 1. For c, it is missing the factor x, 1 factor x minus 1, and a factor x plus 1. For 1/2, it is missing the factor x and x plus 1. And for e, it is missing the factor x and x minus 1 cubed. We then distribute these factors and compare the two numerators using like terms. There are 3 unknowns, so we would need to set up 3 equations. Multiply this out might be a lengthy process, so we're going to use a shortcut. This is true for all x. the left equal the right hand side. We already plugged in x equals 0 and x equals 1 earlier to find the coefficient a and d. This equation is true for all x, and their denominators are the same already, so their numerator must be the same as well. And since the numerators are equal to each other for any x, it is certainly true for x equal 2. So we plug in x equal 2 to the left hand side, and 2, the same number 2, to the right hand side. The two numerators must be the same. The left hand side is 11, and the right hand side can be simplified easily as 2 minus 1 is 1. So the first term is minus 1 times 1 times 3 minus 3, plus the second term, 2 minus 1 is 1, 1 squared is 1, 2b times 3 is 6b. The next term, 2 minus 1 is 1, so 2c times 3 is 6c. The next term, 1/2 times 2 is 1, 1 times 3 is 3, and the last term, 2 minus 1 is 1, 1 times 2e is 2e. Simplifying this, we have 11 equals 6b plus 6c plus 2e. This is one of the three linear equations that we will need. There is nothing special about this number x equal 2. We only chose it because it is convenient. We could have plugged in x equal to 0 and x equals 1, but we already used them. We might want to try plugging x equals -1 next. On the left hand side, it is -1 to the fourth minus -1 cubed plus -1 squared minus -1 plus 1. And plug in -1 to the right hand side as well. But when we plug in -1 into the first term in the numerator on the right hand side, -1 plus 1 would make the term disappear. -1 plus 1 would make the term disappear. 0 times anything is 0. -1 plus 1 make the term disappear. -1 plus 1 is 0 times 1/2 x is 0, make the term disappear. What is left is e times -1 times -1 minus 1 cubed. The left hand side is 5, and the right hand side, -1 minus 1 is -2, -2 raised to the third is -8, -8 times -1 is positive 8, 8e. Thus, e equals 5/8. Notice that if we were to factor out the numerators before and cancel the x plus 1 factor, we could also use the covered up method to find the coefficient e as well. To find the coefficient e, we cover the factor x plus 1 and we plug in -1, which is precisely this. If we were to plug in -1 while covering the factor x plus 1, we would have -1 to the fourth minus -1 cubed plus -1 squared minus -1 plus 1 over -1 times the quantity -1 minus 1 cubed, with this factor being covered. That would give us the coefficient e, and if we did that, we could have saved some step. The equation wouldn't be this long if we had the coefficient e. Now that we have e, we also want to update this equation. 11 equals 6b plus 6c plus 2e, but e is 5/8. So this is 11 equals 6b plus 6c plus 10/8, which is 5/4. And so 6b plus 6c equals 11 minus 5/4, which is 44, minus 5, which is 39. 39 over 4. Next, we plug in negative 2 to the numerator on the left-hand side. And we also plug in negative 2 to the right-hand side and equate the two numerators. The left-hand side is 31, and the right-hand side, negative 2 plus 1 is negative 1. Negative 1 times negative 1 is positive. Negative 2 minus 1 is negative 3. Negative 3 to the third is minus 27. The next term, negative 2 plus 1 is a negative. Negative times negative 2 is positive 2. 2b. 2b times minus 2 minus 1 is minus 3. Minus 3 squared is positive 9. 2 times 9, 18. 18b. The next term, negative 2 plus 1 is negative. Negative times negative 2 is positive 2. Minus 2 minus 1 is minus 3. Minus 3 times 2c is minus 6c. The next term, negative 2 plus 1 is negative 1. Negative 1 times negative 2 is positive 2. 2 over 2, 1. And the last term, negative 2 minus 1 is negative 3. So that would be negative 3 to the third, negative 27 times another negative 2. 27 times 2 is 54e. But remember, we have e already. E is 5 over 8. Simplifying this to get 18b minus 6c equals 93 over 4. We have a system of two equations. One is 18b minus 6c equals 93 over 4, and the other one is 6b plus 6c equals 39 over 4. Solving this system of equation using elimination method, we end up with 24b equals 33. And so b is 33 over 24 divided by 3 top and bottom. We obtain 11 over 8. We then plug in b equals 11 over 8 into one of these linear equations to find c. We will see that c is 1 over 4. Finally, the partial fraction decomposition of the given rational expression is negative 1 over x plus b over x minus 1, but we found b. b is 11 over 8 plus c over x minus 1 squared, but c is 1 over 4 plus 1/2 over x minus 1 cubed plus e over x plus 1, but we found e as well. E is 5 over 8. We are done with the problem because we found the partial fraction decomposition, but if this were an integral problem, we can now find the antiderivative of each of the terms easily using either the natural log or the power rule.